All right, so in section 3.1, right, we talked about one-to-one functions. We introduced the idea of an inverse. And so now what we're going to do is introduce a completely new type of function, which is an exponential function. And then we're going to learn about what the inverses of exponential functions look like. And you're going to find out that they're some form of a log function. So before we can really dig in to exponential functions, we need to make sure that we're all on the same page of the rules of exponents themselves. So when you're solving equations using exponents, the biggest thing that gets everybody in trouble is they do not know the algebra they're allowed to do, all right? So when we work with exponential functions, all right, we need to make sure that we understand all the properties of exponents. So if we take any number and we raise it to 0, right? So we put 0 in the exponent. It doesn't matter what the base b is. B is going to be a constant. This number will always work out to be 1. And I've seen some kind of weird explanations for this online, and none of them ever really kind of made sense to me. But the way that I like to think about it is if you have, right, let's say you have b squared, right? Well, that's b times b, right? You have a string of 2 b's, right? There's always, like we've talked about implied numbers before, where when we do like a square root, there's an implied 2 out front, right? If I just write the variable x, there's an implied 1 out front. So there's actually an implied coefficient of 1 here. I could actually say, well, this is 1 times, right, b times b. We just don't write the 1 because it's silly. We just understand that that 1 is there. So if I were to do this, if I said, well, I have b cubed, then I'd have 1 times 3b's, right? This could be a 2, right? Then that would be a 2. So that means over here, there's like an implied 1 right here because I don't have any other coefficient in front of this number, right? So if you look at 1 times b, right, then that's just a string, right, of 1b. Well, if you have, let's see, this is b to the 1. So we just have 1b on the right-hand side, right? And the way I like to think about this, well, if I have b to the 0, well, then I still have my 1, right? There's still a coefficient there, but all I have left is on the right is the 1. There are just no b's to multiply by. It's not 0, I'm not multiplying by 0. I'm just saying I don't have any b's. So if you kind of look at the pattern that you can do, if you keep upping the exponent, the number of b's you string along. And so to me, the reason it works out to be 1 is because, well, there is a 1 in front of the number. Now, if I wrote this expression as 3b to the 0, well, then the answer would be 3 because it would be 3 times 1, right? Because b to the 0 is just 1. So it does not matter what that base b is. If you raise any number to the 0 power, the answer is 1, right? Unless we shove a coefficient out front, and then it's 1 times that coefficient. All right, so the other properties of exponents, well, if we have a number b raised to the n, and we multiply it by that same number b raised to the m, then we add their respective exponents together. So the example that everybody should know, right? If I say, well, what's x squared times x cubed, pretty much everybody in here would give me x to the 5th. And if I gave you that example, everybody would tell me x to the 5th, but if I asked you what the rule is, most people couldn't tell me the rule unless they saw that example first. So one of the nice things about these exponents is if you have a really basic example in your pocket of how it works, even if I make it more complicated, you're still just simply adding the exponents together. So if we divide, right, b to the n over b to the m, we subtract the bottom number from the top. So that would mean x to the 6th divided by x to the 5th is just going to be x, because you would say the top number minus the bottom number, right? And then some of you may have, like when you start learning how to cancel things, a lot of you would just go, oh, I can cancel x to the 5th out of the top and the bottom. You can do that, but what you're literally doing is subtracting the things you took out of the denominator from what you took in the numerator, okay? Another thing we can do is we can say, well, if I take a number raised to a power, and then I raise the whole quantity to a power, well, then we multiply our exponents together. And furthermore, I'm allowed to switch the order. That's the same thing as saying taking b to the m and then raising it to the exponent n, because all I'm going to do is multiply the two numbers together, and you're allowed to multiply in any order you want. So if we had x squared, right, and we cubed it, that would work out to be x to the 6th, and that's the same thing as taking x cubed and then squaring it. So you can actually switch the order that you write it in that case, because you can multiply in any order. If we have two different bases, but they're raised to the same exponent. So if I have a to the n over b to the n, well, that's the same thing as saying a over b all raised to the n. And these algebra properties seem kind of silly right now, and they probably don't even look like algebra, but when you're solving an equation involving exponents, they come in really handy if you know all the rules. The last one is if you have b raised to a negative exponent, you're allowed to rewrite it as 1 over b to the positive n. So the way you want to think about exponents, we typically say when we're doing a problem, whatever you do to the numerator, you have to do to the denominator, right? With exponents, there's actually kind of an asterisk by that. You are allowed to take anything in the numerator and move it to the denominator and vice versa, but every time that term crosses the fraction bar, you multiply its exponent by -1. So if it's b to the negative n in the numerator, well then when I moved it down into the denominator, I multiplied negative n by -1, and that's what made it positive n. So that means, conversely, if I have a negative exponent in the denominator, well then I'm allowed to move it into the numerator and make it positive by the same idea. So anything can move from top to bottom as long as you adjust its exponent accordingly. And these rules will come back again and again and again in future math classes, and I don't care what class I'm teaching every semester, I have to run back through these again. We use them a lot in Calc 2, we use them a lot in Calc 1, but they do come back, and it's usually just making really silly mistakes, not understanding how exponents work. All right, so let's talk about exponential functions. So exponential functions are functions where the variable is in the exponent. So example, something like that. So a, the base, is a constant number, but the variable is now up in the exponent. Up until now, primarily what we've seen, and there's no real formal name for this, but I'm going to call it a power function, right? That's a function where the variable is raised to a power. Right? So you should be able to see the difference in those two expressions. And a power function, the variable's in the base. That's primarily what we've worked with so far. And then the exponents are constants. Now we're going to look at things where the base is a constant number and the variable is what's changing. So one of the things that you'll see is that exponential functions, especially when those bases are numbers bigger than 1, you'll see they grow much faster than power functions. And then if we give them a base of a number less than 1 and they're getting smaller, they decay much faster than power functions. So they move very, very quickly, and we can see that by comparing two different functions together. So let's look at x squared and 2 to the x. Oops. And we'll just go up to 6 for now because I don't know how far I can remember all my stuff. So if we plug in, I'm sorry, I was still going. All right, so if we want to plug in -1 into these two functions, well, -1 squared is just going to be +1, right? But 2 to the -1 is actually going to be 1/2 because you can move the 2 to the -1, you move the 2 into the denominator to make it a positive value, right? Because that's what we said about negative exponents, right? If we plug in 0, well, you get 0 when you square 0, but 2 to the 0 is 1. So it kind of looks like already that, when we get, you can see if you've got any negative numbers here, x squared is going to be much bigger, right? Then because everything 2 to the x is going to turn into a fraction, right? So if I plugged in -2, I'd get 1/4. If I plugged in -3, I would get 1/8, right? But once you start crossing over into positive numbers, it looks like right out of the gate that 2 to the x is winning, okay? But then what happens when we plug in 1, right? So 1 squared is 1. 2 to the 1 is 2, so it still looks like it's doing pretty good. 2 squared is 4. Well, this is also 2 squared, which is 4, so it's kind of caught back up, sort of like a race, right? Then x squared becomes 9, and 2 cubed is only 8. So it looks like that the parabola is winning now, right? It's kind of taken over. But then look what happens next. So 4 squared is 16, and 2 to the 4th is 16, all right? And then when we square 5, we're going to get 25, but 2 to the 5th is 32. 6 squared is 36, but 2 to the 6th is 64. So what you can see is that even though it starts really small, right, the 2 to the x function is doubling every previous y value. So you went 1, then you got 2, then you got 4, doubled to 8. So the next one, once we get past 64, would be 128. Then we would see 256, right? And so if I go, let's go 2 more, just for funsies, all right? 7 squared is 49, right? 8 squared is 81, but this is 128, and then 256. So that 2 to the x just takes off like a rocket right after x equals 4. So if I graph these two on the same graph, you would actually see that they intersect twice. They intersect when x is 2, and they intersect when x is 4 because they have equal y values there, right? And then the exponential function just shoots straight up while the quadratic function just continues to grow pretty slowly. So I'm going to make a very poor attempt to sketch this and show you what this looks like. So the quadratic, right, looks something like this, but the exponential function does something like this. So it almost looks like a vertical line. It is tilted outward, but it's just growing so steeply that when you only look at this small little portion, it looks vertical. So where it's crossing, right here in right here, this is 0.2, comma 4, and this is 0.4, comma 16. And then you can see everywhere beyond x equals 4, the red line is bigger than the blue line. And that's what this was saying. So one of the things that you'll learn if you ever make it all the way to, well, in Calc 1 you'll deal with it too when you start talking about limits. You'll see that exponential functions will dominate power functions over long periods of time. So one of the things you'll do in calculus is you'll look at limits to infinity. And what you're doing is, how does the function behave when the numbers get really, really, really big? And then you might also look at it, how do the numbers behave when the numbers get really, really small? So out at negative infinity. And so when you're comparing two functions like this, you would see that the exponential function would dominate the power function as it got bigger. And you would see that the power function in this particular case would dominate as this thing gets to negative infinity, because these numbers are just going to get closer and closer to 0. Because we would get a half, a fourth, an eighth, a 16th, a 32nd, a 64th, right? So they get big really fast and they get small really fast, right? So the base of the number is actually going to determine whether or not the function is getting really big or really small. So we have a growth function when b is greater than 1. Notice there's no equal to sign there, okay? If b equals 1, then you just get 1, 1, 1, 1, 1, 1, 1 out forever, right? That doesn't make any sense. So the base of an exponential function can never be 1, but if it's greater than 1, then this thing is going to grow. And it's going to increase over time. And if we don't put a coefficient out front, if I just want to graph b to the x, the graph is going to look like this, where the intercept here is 0, 1, because b to the 0 is 1. We have a decay function if b is between 0 and 1. So b has to be positive, right? And so b could be something like a half or a third, right? Or a fourth. And if you multiply a fraction that's less than 1 by itself again and again and again, it's going to get smaller and smaller and smaller. And that's what we just saw with 1/2. It would just keep chopping it in half again and again. And that could kind of go on forever. So if you graph a decay function, once again, we're just going to graph b to the x, but b is a number less than 1, it will decrease very rapidly. And so what it looks like is, it almost looks like we took the growth function and we flipped it over the y-axis. And that's not what we did specifically, but that sort of is the same effect, right? We took a small number, and we multiplied by itself and made it smaller and smaller and smaller and smaller and smaller and smaller and smaller. Okay. So let's look at doing some algebra with exponential functions. So we want to solve the following expression for x. So this is what I was saying by, if you really understand those exponential properties, you can do this without much issue. But notice that they're not just simple things like 2 to the 3, 4 to the 5, like we've got expressions up there. So there is one more rule of exponents that's sort of my favorite. I use it all the time. And whenever I'm doing a problem like this, I always check. And you'll see this kind of rule will come up again a little bit when we look at logs. So if you have b to the n equals b to the m, so the bases are the same, but the exponents are different, right? And we know that b is not 1, because if b is 1, then m and n could be anything, because 1 to the squared is the same thing as 1 cubed, right? So if this is true, then n has to equal m. So if I have 2 to the x equals 2 to the y, then x and y have to equal each other, right? As long as that base is not 1. So the game here is, when you're doing a problem like this, is find a common base. If you can find a base that both of these expressions share, we can rewrite it and try to get it in b to the n equals b to the n form. So what number do you think 27 and 81 are going to have in common?
9.
They have 9. Can we go lower? 3. Let's go prime. Let's get it as far down as we can, right? So they're both divisible by 9, right? But 9 times 3 is 27, right? And 9 times 9 is 81. We want something we can raise to an exponential power. That's why you want to go as low as you possibly can with the number, okay? So 3 is what to 27? How do you get to 27 out of 3? 3 to the third, right? 3 times 3 times 3. So you want to think of 9 as 3 times 3, not 9, right? So if 9 times 3 is 27, then 3 times 3 times 3 is 27. So what I can do is I can take this 27 and I can say, well, that's 3 cubed, right? And then I'm going to raise it to everything else, right? So then how do I get to 81 from 3? 3 to the 4th, okay? So 81 is now 3 to the 4th times it. So all I did was replace those two numbers with how to find them in terms of 3, right? So then I'm still not quite to where I want to be. I want it to be 3 to the stuff equals 3 to the different stuff, right? So I can actually simplify each side by saying, well, I have an exponent raised to an exponent, so we multiply the exponents together. So that means on the left, I distribute the 3 across. And this is what I meant. Those rules are the rules, right? We said if it were x squared cubed, right, we would just say x to the 6th. So this becomes 3 to the 9x plus 6 on the left. All I do is distribute the 3. On the right, I'll do the same thing with the 4. I just multiply the 4 across. So on the right, I have 3 to the 16x plus 20. So now I'm right where I want to be. I've got 3 raised to some stuff equals 3 raised to some different stuff, right? And 3 is definitely not 1. So now I can say, well, those exponents just have to be equal to each other. So I can invoke this rule and say, well, that means 9x plus 6 has to equal 16x plus 20. And then I can just continue solving for x. Does this not make sense to anybody? You just drop the exponents down. Okay. And if you don't always see this, play around with some numbers. You'll see you cannot come up with any other combination where 3 raised to something equals, if those two numbers are not the same thing, or those two expressions are not the same thing. It's just not possible. So if we want to solve for x, I'm going to subtract 9x from both sides. So 16 minus 9 is 7. Then I'm going to subtract 20 from both sides. I get negative 14. So negative 2 equals x. So personally to me, these are just games and puzzles. If you have a finite list of moves you can make on a problem like this, that's all you can do are those things I gave you on the list, and it's just playing around with those moves until you can whittle it down to get where you want to do. But this guy right here is my favorite, and every time I'm doing one of these problems, it's always, can I find the same base? And if I can, always take that path first. If not, then later we're going to see when we have problems like this with different bases, we're going to have to use something called inverse functions to try to unwrap it, and we're just not there yet in this section. All right. All right, so I want to graph both of these expressions. And I'm going to graph them on two separate graphs. So the first one is just your standard exponential function. It's just 4 to the x, right? It's just like we said b to the x earlier. So the first thing you want to do is you want to look at the value of b, which in this case is 4. So it's bigger than 1, so we know this thing is growing really quickly. So when we graph it, we know it's going to be a growth exponential function. So one of the things you can do, rather than trying to, unless you're on an actual piece of grid paper like on Alex where you have to plot the points, if you're just sketching something on your own, you know the shape of the graph, so just draw the graph and then label things around it to make it so that way it looks nice. That's what like zoom fit on your calculator used to do on your thing. So it's typical to label the intercept, you know, some kind of attribute, and we know that if you plug 0 in, you're going to get 1, because 4 to the 0 is 1. So this would be, right, the graph of y equals 4 to the x. Well, the second equation, right, knowing what we know from last unit, says, well, the base graph there is 4 to the x. It says shift it to the right 2 places. That's what happens when you plug x minus 2 into the function. And then adding 5 on the outside of the function says shift it up 5 places. So if I take this point, 0, 1, and I shift it to the right 2, right, its x-coordinate becomes 2. And then if I shift it up 5 places, right, I would add 5 to this. So this point here is 2, 5. So we shifted it over to, 2, 6. Right? The original graph had an asymptote at y equals 0, right? It got really close to the x-axis, but it never touched it. So if the whole graph got shifted up 5 places, then that means we have an asymptote up at 5, because it was at 0, but it got shifted up 5 places to 5. So my new graph looks like this. So knowing our shifts and our translations, and this is a 6, right? Knowing our shifts and translations, we can still flip things, shift it left or right, move it up or down, stretch it if we want it. But very quickly, you should be able to move these exponential functions around, and you should recognize what the inside of the function is versus what the outside of the function is. So on an exponential function, the inside is always going to be up in the exponent, because that's where the variables live.
Did you stretch it from a y value, like the y on the outside?
Mm-hmm. We can add if you add a variable up front, it's going to adjust the intercept that you have. Mm-hmm. Okay, so let's look at a pretty standard form. Right, so if we want to allow for every eventuality, right, we could say, well, we could have an expression of the form a times b to the x. So only b is being raised to the x, not a. A is going to act as a coefficient. So if I have an a is going to be the y-intercept. And that's because if you plug 0 into the function, you will get a out, because b to the 0 would be 1, and then you would multiply it times that value a. So what this allows us to do is shift it, the intercept, up or down along the y-axis, right? So it normally would be at 0, 1 if it was just b to the x, and the a pushes it up or down depending on its value. B is still the base, and x is obviously the variable. So what I want to look at is, let's say that a population starts out with 500 people and grows by 10% each year. Let's find an expression for P of t. So the initial value that we were given in the problem is 500 people when they start counting. So that would be, well, we'll call that time 0. And then we start measuring every year after that. So if we want to use this general form, we're given any other information, so we just would start with this general form. And we would say, well, at time 0, right, we know we have 500 people. So that would probably be the A value. The question here is, what is B? How do we take that 10% growth and figure out the value of B?
1 plus the 10%.
It's 1 plus 10%, okay? So B is actually going to be 1.1, all right? And more specifically, it's 1 plus 0.1. So it's 1 plus the rate of growth in decimal forms. You always have to put the decimal or the percentages in decimal form. So what's actually happening here? So the reason you need 1.1 is, first of all, it's growth, so you better have a base bigger than 1 or it's not going to get bigger, right? The 1 is letting you keep everything you already had. The 10% is just adding 10% of what you just multiplied by. So if you get a raise of 10% at work, what you should really do is multiply your current salary by 1.1 if you want to know what you're going to make next year, because you get to keep all the money you currently make, right? That's what the 1 does, and then add the 10% to it. If you just multiply by 0.1, that's just only telling you the additional money that you're getting. It's not going to tell you the full amount. So whenever you see a percent increase in something, if you want to know what the total new amount is, you should always do 1 plus that rate. Okay? And so the 1's letting you keeping what you already had, and the rate is adding the additional amount to it. Right? And the other reason we have to make sure we add these numbers together is, well, then the next year, let's say, so 10% of 500 is 50, right? So that means in year 2, there should be 550 people in this town. Well, in year 3, if it's growing by an additional 10%, it's 10% of 550. It's not just adding a flat 50 people every year. If it was just adding 50 people every year, well, then we'd have a line, 50 people per year, and that would be a linear. But exponential growth lets you just keep growing based on what you already had. So that's what the 1's keeps what you had the previous year, and the 10% is going to take 10% of that new variable. So P of t is 500 times 1.1 to the t. So if I give you an expression and I ask what the growth rate is in this expression, well, 1,000 is just whatever the value was at time 0, right? The number inside is the base, right? And the rate, you take the stuff in addition to the 1, because all the 1 is doing is keeping what you currently had. So if you have an R value here, right? So 1.035 is 1 plus 0.035. So R is this. This is a decimal, or a percentage, excuse me, in decimal form. So if I want to actually return the percentage, I multiply times 100, and I see this rate was 3.5%. So a lot of times in problems, we're going to describe percentages as percentages, but you have to know you have to convert them into decimals. And where that'll really get tricky is if I give you a problem and I say this bank account grew at 0.02%. And then you would have to move the decimal 2 more places. So a lot of the problems, it kind of annoys me, but a lot of the problems we'll do in this section when we're going to start talking about money and finances a little bit, the interest rates are ridiculous. I mean, like, no one gets those rates anymore. I mean, it used to be a thing, but like no one gets like a full even percentage point on like a standard personal savings account. You're getting like fractions of a percent in your account every year, but those numbers are so tiny that you can't really visually see the graph. It doesn't really work out that well. But yeah, I mean, we'll do problems where it'll be like a 7% interest rate, and it's like, no, that's like the other way around. That's like what credit cards would charge you, so, or more. So it's a little bit annoying. So watch out for some of the problems because the rate will actually be a decimal percent, and then you have to still convert it back over. So I think I have an account that gets like, it had an introductory rate of 0.033, and then it dropped down to 0.025, and I was like, that's 1/4%, and then when you multiply it out, it's 0.00025. Like, it's just absolutely ridiculous. So I think I get like a couple dollars a year off that account. All right, so let's, I think, pause it here. This is a good place to stop.